This is the fifth and final section or module in our chapter on magnetic fields, chapter 27. And here we're going to take up the concept of the motion of particles in a magnetic field that are charged. And this will be section 27.5. Now, I've written these equations without their derivation here. If I have a particle that goes around in a circle in a magnetic field, and let's imagine that the magnetic field, for example, is coming out of the page, and therefore it has a force that's going to be in the to the right, so there'd be V cross actually going down. So B goes down, that would be a magnetic force that goes out, but it has a centripetal force that pulls inward. And so what we want to do is for a circle of radius r, where a charge q, mass m, is moving with a velocity v in a circle, we want to look at how a magnetic field can force that particle to stay in a perfect circle. And it will stay in a circle. And I've derived these equations in the following, so this might be of use to you. First of all, looking at this, we know that the centripetal force is mv squared over r. You recall that from when we talked about centripetal forces. So this particle wants to fly out in that direction, has a force in the outward direction. And now we need a force in the inward direction that would be comparable to that. And that magnetic force would be Q times V cross B. We're going to make V and B perpendicular here, so it means that if V is going this way, we're going to take B as being downward. Then V cross B, the way V cross B goes, is V cross B goes inward, pulling the particle inward where the centripetal force pulls it outward, and these two forces will match if this is a stable configuration. Therefore, we can write mv squared over r, that's the centripetal force, equals to the magnetic force, qvb. Well, there's a power of the velocity that cancels both sides, so we've canceled the square here and the velocity here. Then we solved for the radius by taking mv over here and dividing through by qb and putting the r over here. So we get the first result right up here, that r is equal to mv divided by qb. And that gives us the radius of the circle for a particle of mass m, for a given charge, for a given velocity, and for a given magnetic field, that charge will run around in a circle of this radius if it's in that magnetic field. We know, believe it or not, that's a pretty powerful result. The reason it's a powerful result is if we're looking at a photograph and we see a charged particle going around in a circle, and we can measure the radius, and we can compute the velocity, and then we can compute, knowing the magnetic field and knowing the velocity and seeing the radius, we can compute the ratio of the mass to the charge. That's called the charge to mass ratio. And says, for a given charge, how much mass do we have? This was some of our earliest work on elementary particles, understanding what the masses were and what their charges were, or given their charge, compute what their mass is. Well, the next equation we need to know is with what period do these particles go around. So watch me as I compute the period here. We know that the velocity going around is the distance around the circumference divided by the period of motion. So it goes around one circumference, 2 pi r, in a period of time t. That's the velocity, distance divided by time. That's kind of a neat expression. We've used that before in our rotational motion to connect the period to the velocity that's tangential for a circle. Now, we can solve that for t, and we get 2 pi r over v, obviously. Now we're going to substitute in the r that we just had. So we're going to write 2 pi times the r from right here, mv over qb. mv over qb, and times the v that's down here. Well, this v cancels this v and leaves us with the equation that the period of the particle going around in a circle in a magnetic field is given by 2 pi times the mass divided by the charge times the magnetic field. This gives us the radius of that motion. And that really tells us how these charged particles move in a magnetic field. So in general, what you have is, if you have, say, a magnetic field, and again, we're going to take that magnetic field as, say, going downward. We do that represented by kind of an X. That's magnetic field going into the paper. I'll put N there. And if that's the case, then V cross B would be attractive there. So we can say, what would this particle do? The answer is it runs around in a circle. So if I have a magnetic field, say going downward, and I have a bunch of particles, they'll all run around in circles of different sizes. Depending upon what? Depending upon what their charge is to their mass and what the magnetic field is. If they're all the same charge to mass ratio, if they're all, say, electrons, then they're all going to have the same mass and all have the same charge. If B is constant over this whole region, then in fact the periods will all be the same. But in fact, if they have different velocities, they will have different radii. Some will go around their circles very fast there. They go in larger ones here. And so depending upon the velocity, they have a larger radius or a smaller radius. So we can determine that charge to mass ratio by looking at the period and by the rotation. Now, if the magnetic field is off to an angle, it turns out that that circular motion is added to a constant velocity because there's no force in that direction. That's the other part of the cross product. So in fact, a charged particle spirals around a magnetic field line. Remember, the magnetic field here is going into the paper everywhere. And so what we have is this charged particle goes around those magnetic field lines. But if it had a velocity that also pointed somewhat into the paper, not just perpendicular to the magnetic field, then we would see that that particle would move at a constant velocity downward while it circulated around the magnetic field line. That would give it the appearance of being like a spring that was coiled. This is in a helical motion. And that's exactly what happens with the Earth. And the Earth's magnetic field, as a particle comes in, it goes in a circle around that magnetic field line, and it focuses that charged particle up into the North Pole, where it hits up there with the aurora borealis, as I mentioned before. Now I want you to note, we talked here about the helix. No work can be done on a free charge moving in a magnetic field. Now that seems really strange, but it turns out that the force is always perpendicular to the velocity. If I look at the equation that we had earlier, F is equal to QV cross B, you'll notice the force, since this is a cross product, is perpendicular to V and perpendicular to B. Therefore, since work is the infinitesimal distance, dr, cross F dot dr, I should write it, F dot dr, and this is dr over dt. Because of this dr and the F being perpendicular, this is always 0. Therefore, a free charge, a magnetic field, cannot do work on a free charge. Well, those of you who are really paying attention think, whoa, something is wrong here, because we have motors, and in motors we have currents, and there are forces that exist on those wires, and that's what makes the motor turn around. So how does that work? Well, we'll learn about that later when we look at the details, but we'll find that they're not free particles, they're in wires, and that causes, the being in the wire causes a constraint.